science of fracture management, but specifically about plates and plate design. The reason why is this is a topic that if you haven't put any thought into, when you get hit by it, you will be shocked and you will not respond well. So it's very important that we kind of go through this. It's also a great topic because it does cover quite a number of chapters in basic science and also in fracture management. And you can take this from plates to other forms of fixation and other forms of implants, and you can use the same basic science knowledge and apply it in different ways. So I really do recommend you do spend some time focusing on this area as well. So first of all, my declarations. These are my opinions and do not represent any organization. I have no financial interests to declare. Pictures of implants are in no way an endorsement of any of the implants. All pictures taken from the internet as fair use for educational purposes. There's our first picture. Design the perfect plate or delivery device. And that's the response I want to try and avoid. I don't want you saying things like, I use X plate because I think it's perfect, or I know it well, or my hospital uses it, or the rep tells me it's perfect. Do that and you'll see, remember this image of me smacking my head and getting upset with you guys. Okay, so the answer is always prepare a simple sentence for any question like this. Try and divide your answers into headings and then work on those headings. So the design of my implant would require consideration of many factors, including material properties, structural properties, interface fixation, and modality of use. I would usually say modality of use first. Depending on how I'm going to use it, then I would decide what material, structural, and interface fixation devices I need. But I'm leaving this to the last because it's a bigger topic and it's worth kind of quizzing you guys on it down the line. So, material properties. You need to discuss Young's modulus, elastic, plastic, yield points, the brittleness or ductile features of your device, and the toughness and hardness of them. And remember, material properties are independent of shape. So, and my ideal material would be something which is bio-inert, reliable, easily manufactured, and sterilizable. It should be a reasonable price, or a price which is acceptable considering we put so many into them, and is corrosion resistant. Ideally, it should be ductile. We need to know how ductile we want it, and the toughness and hardness. These are two different concepts, by the way, toughness and hardness. We'll come to that in a moment. Examples of materials we use commonly: stainless steel 316L. The 316, this is quite an important question. They do ask you about this quite frequently. What does the 3 stands for? Molybdenum, 3%, nickel, 16%. And the L stands for low carbon, which is any metal, any stainless steel which has less than 0.03%. Now, this is quite an important concept. Why do we use the 316 series? Why do we use the 300 series, but specifically the L series? The reason why is the low carbon is more resistant to corrosion in the human body because of sodium chloride in the body. So this is a plate or metal that is used in the oceans and seas by engineers there, and it has the same resistant properties as it would have in the ocean because our bodies are essentially salt. So that's quite a trick to that question, but once you get that one out, you're saving yourself trouble. The next question they usually ask is, what is titanium alloy, which we use the 6Al for V, aluminium 6%, vanadium 4%. Know that vanadium does have some potential ion reaction problems, and that's potentially a question that can be asked, especially if you have scratches on your titanium plate or titanium rod. But the nice thing about titanium is it's self-pacifying. Okay, so that's quite a useful feature of it. The other advantages with titanium is that its Young's modulus of elasticity is closer to bone, and therefore it's more ductile, and also works better in terms of giving you working length and things like that. However, in the conversation about this, the pros and cons, you can say stainless steel has many ways of modifying its modulus of elasticity, and we'll come to those questions later. The advantage of stainless steel is it's cheap, it's readily available, we know its properties, and it's consistent throughout. Cobalt chromium alloy is the other one we use, but in plate fixation it's rare that we use it. It's more for its surface hardness that we use it for. So what is modulus of elasticity? So if you take a diagram and give yourself force and displacement, your slope gives you your stiffness. That's force over displacement. Very simple concept. Now we're going to make it a little bit more complicated and talk about stress and strain. Force is, your stress is your force over an area, which is newtons over meter squared, or otherwise known as pascals. And your strain is your change in length or height compared to its divided by its original length, and it has no units because you're dividing distance by itself. Okay, I'm just going over this very quickly because you do need to know these definitions very well and be able to spill them out very quickly, because otherwise you'll get stuck. So then, taking that same diagram, instead we use stress and we use the bottom to strain, and we've got our slope, which is Young's modulus of elasticity. The next thing to say is that the common materials in orthopedics, there's your numbers. Do you notice that we say titanium has a closer modulus of elasticity to cortical bone, but the reality is it's a huge difference between the two. So I'm not 100% convinced. This is my personal opinion. I'm not 100% convinced about titanium's advantages in these situations, especially in plates as opposed to nails. And then this diagram, it's pretty much everywhere. I do recommend you memorize it because it has come up in the exam scenarios where they've put that picture in front of you and said, what is 1, what is 2, what is 3, 4, and so on. Essentially what they want to know is, do you understand the relative Young's modulus compared to bone, and where would you imagine bone would be, and where each of the metals and other orthopedic implant material would be. Okay, now we said we'd talk about a few of the properties of a stress-strain graph and what they mean. So the elastic property is the area where Young's modulus exists. It's where you get equal and straight line, essentially, where you get an equal between stress and strain, and that's this point here. After that, you get plastic deformity, and for the purposes of this, I've drawn this quite severely, just so we can show the different parts. So the yield point is the point where you move from elastic to plastic. Your yielding area is the area where you're starting to lose lose hardness. But then you start to develop a strain hardening environment. This is important to know because this is in cold welding steel, cold working of steel. This is where you can get ultimate tensile strength in your prosthesis. So you can cold work this. What this does is it creates the annulate molecules within your stainless steel to align up more well, and to prevent defects, and to create a more compact spacing of the molecules together. And this gives you your most strongest or hardest material possible. But anything after a certain point, anything after ultimate tensile strength is necking. And we do see necking in the early stages of failure of plates and or prostheses. And finally, fracture. Now, I did say I'd mention the difference between strength and hardness, of the properties of strength and hardness. So strength is everything, the area underneath that graph. So the area underneath that graph is the strength of any metal. What it represents really is the energy required to create a fracture. While the hardness is a surface property of the material. So do make sure you understand the difference between those two, and it's quite important that you want to be able to throw out those definitions very quickly. Now, so far we've talked about the stress-strain graph and its modality and use in orthopedics and trauma. We've also talked about the different metals we use, and we've shown we know something about them and why we use different ones. You can even go through the advantages and disadvantages graph in Ramachandran's book, and you'll find that that you'll be on safe ground straight away. So now we go on to structural properties. These include bending stiffness, torsional stiffness, and axial stiffness. So bending stiffness is pretty straightforward. By the way, this is all dependent on the shape of the material, okay? So bending stiffness is essentially if you take any length of any material and you put pressure on whatever the length is and bend against it, that's your bending stiffness. Torsional stiffness is twisting of that same material, and axial stiffness is weight bearing on the length of that material. But essentially, they're all dependent on your cross-sectional shape of your property. Okay, so your design of your implant allows resistance to bending. If, for example, if you're using a rod, if you increase the radius of the rod, you have a more stiffer construct using your second moment of inertia. That formula is pi r to the power of 4 divided by 4. And that's quite a significant number to remember, because you literally are multiplying, if you double something, you're multiplying it by a factor of 16. Of a plate or any metal bar, you're talking about width multiplied by the height, or in this case d, to the power of 3. Now that's an important concept to understand, because if you ever look at building sites, you'll always see that there are girders in the building sites. And you wonder, why would they use girders? Well, there you are. That's the picture explains it perfectly there, the bottom picture here. The girder itself, you're still preserving the height of your plate. But what you're doing is using less metal. Therefore, you have a lighter construct. And it's an important concept to remember, because you're maintaining the width of your construct, you're maintaining the height of your construct, but using far less metal in that process. The same principle as your hollow nails. Again, less for the same amount of material, you can achieve a more rigid construct by bringing out, using that material as a hollow tube. You can appreciate that there's far more material in this than there is in this. And for a small decrease in the proportion of decrease in the proportion of your moment area. Okay. Now we're going to move on to the next part of this. Remember, we talked about using your girders as a principle, and remember that their height is preserved. That's the same principle behind the low contact plate. In your low contact plate, you can now take away metal, therefore you need less metal, but more importantly, you now have less surface area to pressure the bone. As you can see, the height is still preserved and the width is still preserved, but the plate is missing these small areas here, which represent this area here, okay? And then that same principle we talked about with the girders is still present with your 1/3 tubular. 1/3 tubular is usually 1 millimeter thick plate, but by putting it as a 1/3 of a tube, you're still preserving the height, as you can see on this schematic representation there. Okay. Now we move on to our interface fixation. So we have a choice between conventional and locking screws. The other way to describe them is by compression and using plate friction versus a fixed angle device, okay? Or you can use them in combination. In a conventional plate, you're dependent on your friction interface between the plate and the bone. So what you're doing is you're compressing your plate onto the bone. And once you've done that, you're loading the bone, and then the patient's own load adds up together to create, sorry, apologize, go back. The friction force is far more than the patient's load, therefore your plate construct is going to be preserved. In terms of locking plate and screw fixation, you're locking your plate your screw into the plate. That's what those crosses represent. That's the screw locked into the plate. That's creating a fixed angle device. You're loading your patient's load, and you're overcoming the compressive strength of the bone. Okay, so essentially your locking device is transferring the weight of the bone onto the plate. So in the stress situation, you're doing a patient loading with the different types. You have one option of preloading this, and that creates your interface. So there is a difference between your standard versus locking loading. And to be honest with you, and then this is demonstrating that the pull-out strength of the pull-out strength of this construct is dependent on a single screw each time, and each one will individually fail, one sequentially. While what we see with the locking plates is that you get you have a larger resistant area, but your force requires you to make sure all your fixed angle fixations to fail at one go. So there are advantages to your locking plate. However, it's not necessarily always the right answer for this, and we'll come to why that is the case. So some of the other things we need to consider about in our plate design is preservation of blood supply, and that can be a discussion about periosteal blood supply and centrifugal versus centripetal blood flow. You maybe need to talk about when those two change over, both in terms of childhood or childhood to adulthood, and vice versa in terms of post-nailing or post-trauma. So you have two options. You can use your low contact plate, your minimally invasive or minimally disruptive approach, or you can use your plate as an internal external fixator, though this concept is going out of favor because it's the danger is that you do get a malreduction on your working neck, potentially can be quite long. We'll come to that in a moment again. And then why not use both? So that's what you're going to say in your exam. Those are my options of fixation, but an ideal plate will give me both options. Okay. Then the advantages will be, of course, that you have many more options interruptively, but other advantages include less plates, less equipment required on your shelf. And then you've got pre-countering and countering and fracture fragment specific plates. These are all available, and there are multiple options. And at this point, I would also talk about my distal metaphyseal fixation plates, such as a distal femoral plate with an elongated shaft to allow me to do more complex fractures. I'll talk about my individual different types of plates for my fracture fragment fixations. But again, I want an all dancing, all singing plate, and I would love a plate that will give me multiple options in one plate. And that's where you can talk about your variable angle versus your straight locking systems, and your pre-contour plates specifically for the different types of parts of the body. And then finally, you come to your modality of use. Now, remember I told you I would bring up modality of use at the very beginning of this conversation, because depending on what you're dealing with, that's how you want to design your plate, ideally. Even though you want an all-singing, all-dancing plate, there are some plates which would be inappropriate for different parts of the body versus other plates. So my approach to any fracture is, what is my intention? How am I going to achieve my intention? And how am I going to hold my intention until the fracture is healed? So you need to discuss things like primary healing versus secondary healing. You need to discuss anatomical reduction versus alignment, your rigid fixation versus your relative fixation, load sharing and load bearing, and combinations as demonstrated in the picture on the right. This one definitely needs combinations of different approaches. Okay, so in summary, I would like to say, don't jump on implants. Don't mention names of prostheses. Don't talk about different types of names. Don't bring up companies. the question is not about what implants you know, it's about your understanding of the different topics within basic science. You need to understand the management principles of your fracture. You need to understand what you're trying to achieve with your fracture and what your plate is going to do to help you achieve that, and then design your plate accordingly. Okay? Structure your answer. You don't have to follow this structure, but I would advise you strongly to have a think about how you're going to answer that question. And this question can easily be: design your perfect hip prosthesis, design your perfect knee replacement, design your perfect intermedullary rod. But it's not about which rod you know, it's all about exactly what are the principles behind the design, what are the potential pitfalls, and how you can avoid them. So I want to talk about a couple of things in terms of your intention to healing and primary healing. About your modality of use. So when you're there is a tendency in trauma as well to put up an x-ray of a really difficult looking fracture fragment, and they'll say, how are you going to fix this? The first thing you should always say is, presuming this patient is has been assessed and this is an isolated closed injury, or if they tell you it's an open injury, therefore just assume that, and the patient is neurovascularly intact in a fully consented and draped patient, my positioning is, and from there say my intention of fixation will be this, how I will achieve my goal of fixation is Y, and how I will maintain that fixation is length of the construct. That's the scrub nurse.
Yeah, start.
Samir,
Okay.
Samir,
Yeah. Hi.
Yeah, Samir, we can see Samir now. So Samir,
Yeah, to the power 3. That's
The
what
first
drawing.
length is, if you look at the screen, is between the two nearest pins to the fracture site.
Yes.
Your second set of working lengths that you have to think about is between the bone and the bar.
Yes.
Okay? On
Yeah.
each one. Yeah?
Right.
Good. So now, anything else I can do to this construct that will increase rigidity, and tell me why. Back down.
no,
Increasing the height of your between the distance between your two bars, decreasing the distance from the nearest bar to the skin. We talked about multiplanar. Any other things you can do?
Yes, I could increase the thickness of the screws or the pins, and again that would act as to the third power of 3.
Is it to the power 3? Are pins to the power 3?
No, power of 4, because
4.
it's a cylinder shape.
Good. Excellent.
In addition, I could increase the number of screws on each side, pins on each side.
Okay.
Yes?
Yeah, you could, but do you think that's going to make a big difference?
No, that's the least of all of the factors, but that adds as well.
Okay.
I could, we've talked about I could add the thickness of the bars themselves. So instead of using a 5 millimeter, I could use a 6 millimeter.
Yeah, but that's really small, because we've established that the distance between the bars is far more important. Okay.
Exactly. I could use a different material. So instead of using titanium, for example, I could go for stainless steel or even cobalt chrome. And I could,
and or what are these nowadays? Carbon fiber, yeah.
Carbon fiber, yes.
Okay. And anything else? Can you do anything to the fracture?
Yes, anatomical reduction. Well, that adds to the bone stability, and that takes some of the weight. So if you have good contact of the fracture itself, then the device would act as a load sharing rather than a load bearing, which means the amount of forces that goes through the external fixator construct is less because of the contact between the two fragments. So
changing your construct to a load sharing construct will increase your rigidity overall. Excellent. I like beautiful phrasing and beautiful understanding. Excellent. Well done, Abdullah. Okay. Can you think of anything else about this construct which would tell you the working length is shorter than that? If you look very closely over here.
No, I'm not getting anything.
Okay, so the working length of an intramedullary nail is the working length. Take the definition that we already presented. The definition is the unsupported length of the construct. So we have support here, correct? We
Okay.
also have support at the diaphysis of this femur, because that is the
Okay.
narrowest point, and we've tried to get the nail in at the size of the diaphysis, or just a couple of millimeters smaller than the diaphysis. Isn't that right?
Okay.
That's
Correct.
why we
Correct.
1.5 above the size of the nail that we intend to put in, because we want to get
Okay.
it as close a fit but as big a nail as possible.
Okay.
Okay, so that's
Okay.
the working length from here to here. I purposely put this on because I know this is a concept that sometimes
Okay.
we miss in our discussion of these questions. Okay, so if
Okay.
that's the working length from here to here, what can I do to increase this rigidity of this construct?
We've already used a good thickness nail.
Okay, so no, we haven't, but we can use a thicker nail. Yes. Okay. What else?
Okay.
Why does that increase rigidity?
It will decrease the working length.
Not. There's another bigger factor why increasing the size of your nail.
The diameter, yes, to the power of 4.
Is it
Yes.
the diameter or the radius?
Radius, sorry, radius.
Correct. Okay. Anything else we can do to this?
A better alignment and a better reduction of
Okay,
the
so
fracture fragments.
that's exactly the same conversation we had for the external fixator. Yes. Okay.
Yes.
What
Yes.
else? Going back to the metallurgy of this.
Yes, we can use a stiffer implant, a stainless steel.
Okay, that's good. We can do that. Now, that's a question I want to ask you. Do you think this cephalomodular device is stainless steel or titanium, and which would be your preference? Why?
Titanium, because its modulus is more closer to the bone.
Okay. Why? Why do you want a modulus closer to the bone?
We are achieving a relative type of fixation in these type of fracture. So for that, to get a modulus closer to the bone, the implant's modulus closer to the bone, it's better.
And what does that do if you bring your implant modulus closer to the bone?
No.
Okay. What it does do is, first of all, yes, you're correct. It increases it becomes less rigid as a prosthesis compared to, so titanium is less rigid as prosthesis. It is more flexible, but and it has a more elastic properties to it compared to stainless steel. However, it also sorry, I just lost my train of thought. I apologize. We were talking about titanium versus stainless steel, and yes.
So the titanium has the young modulus closer to the bone, and hence it prevents stress shielding. You are using
Exactly. Thank you very much.
You are using this rod as a load sharing device. If you make it very rigid, it will become load bearing device, and it will create stress shielding. Guys, your concept needs to.
Yeah, so I could see 3 X-rays in this. 3 X-rays. The first X-ray radiograph shows the fracture of radius.
Mm-hmm. Anything about that pattern?
In both AP and lateral view.
Yeah.
So this seems to be a short oblique.
Okay, good.
Short oblique.
Yep, brilliant. And what do you think of
So in the second X-ray, I could see there is a lag screw which is placed across the fracture with a neutralization plate with two screws on either side of the fracture fragments, either side of the fracture.
Mm-hmm. Brilliant. So what is the working length here?
So this again is a 0 working length because the fracture is anatomically reduced, and there is a lag screw causing compression.
Okay.
So there will be 0.
But this is a shaft fracture. Why are we going for anatomical and primary healing here?
So the concept in both bone forearm fractures is it is not only the this is the interosseous membrane is also considered as a joint because there is a movement happening there which is a pronation and supination movement, and if there is a malreduction in the length of one bone, it will affect the joints proximal and distal. That is the proximal and distal radial nerve joints, which in turn will reduce the forearm pronation and supination range of motion.
Okay, good. So why not just put a lag screw, and why do you want a neutralization plate? And what is the concept of a neutralization plate? What does it control?
Okay. Yeah. So a lag screw, it provides compression, but it does not have adequate bending and torsional stiffness. So to provide more bending and torsional stiffness, we add a plate, which is a neutralization plate.
Very good. You brought up the exact concepts that I wanted you to bring up, bending and torsional. So if you want to prevent bending, what type of plate do you want to use?
So to improve the bending stiffness, I would use a plate which is thicker with a material which is more rigid, and then
okay, very good.
That's what.
So any other places where we would use a neutralization plate routinely?
Neutralization plates, it can be used everywhere, wherever we are achieving,
What's the most common fracture presentation that you would use a neutralization plate for?
It is like oblique fracture, where I would definitely.
I mean, so what anatomical area? Usually the ankle, isn't that correct? The most common.
Yes, ankle. Yeah, especially on the fibula.
So why do we use a 1/3 tubular as a neutralization plate there compared to using a big LCP DCP plate here?
Majority of the load passes through the radius, whereas in the ankle, majority of the load passes through the tibia.
Good, excellent, and that's brilliant.
Whereas the fibula.
You know what? I don't need to hear anymore. I know you know your stuff. You would literally, that's a minimum of a 6. And if we continued driving you, we probably would have got to a 7.
I think that's quite an